Monday, so I'm a little scratchy today. So bear with me. All right, today is Wednesday. I have 2 more people to interview after class, so I will know by tonight who my student assistant is going to be. So the way this works is once I hire an SA, I'll put the SA into the class roster with instructor privileges to be able to grade homeworks and stuff. And the SA will also set up office hours, so you can, if you have need help sessions when I'm not around, you can do that too. So, like I said, I had 9 candidates. I've interviewed 7. I got 2 more to interview. So, any other questions before we get started today? I've had a couple people who had trouble downloading the lecture notes off of D2L. Is anybody having trouble downloading the lecture notes? I would think not. But yeah, because you're not officially registered, right? Oh, do you know how long it takes? I don't know how long it takes. It shouldn't take too long once you get in the system. If you need and once you get on D2L, you'll be able to download all the old notes too. So. Other questions? See, this one is not the touch screen. I think this one's the only one that's the touch screen. Yeah, no, maybe not even that. Let me move this out of the way because this is, put that up here somewhere. Okay. So today we're going to start finishing up lecture 2, and then we'll move into lecture 3. I guess that's good enough. All right, so one of the things that's kind of fundamental about the way wireless local area networks work is that basically we have the idea of merging multiple users onto the same stream, the same medium. And that idea of putting multiple users on the same medium is called multiplexing. So we have multiple inputs, we have a multiplexer, we have a channel, a link with a number of channels in time, frequency, code or space, and then we have a demultiplexer that separates them back out at the other end. And so typically it's much more cost effective to put multiple users in a single channel, like a fiber channel. And so if I have a really broadband fiber channel, I can put hundreds or thousands of users onto that fiber channel. And that's really the way things are done anymore. Before many of you were born, telephone systems ran over an FDM system where every voice circuit was a 4 kilohertz wide channel, and then they would put all those together in frequency division multiplexing, and then send those out over wider and wider channels. Those are called groups. 12 voice channels was a group. You could have 60 voice channels in a super group, and you could have super master groups. This was all analog way back when. It's really clumsy. Today we do it much more efficiently with digital multiplexing. So the main ways we do multiplexing are frequency division multiplexing, and that's where everybody gets their own frequency channel. We have time division multiplexing, where everybody gets a time slice, and that's the way things are typically done in a lot of media, especially fiber channels. And so this shows kind of what frequency division multiplexing looks like, where we have basically everybody stays in that same channel all the time, and you have multiple frequency channels that can be of different bandwidths, actually, even. So, of course, there's always a problem in frequency. It's very difficult to pack things tightly in frequency. The filters are never perfect, so there's always a bleed over from one channel to another in FDM, which is one of the problems with FDM, is that you just can't pack these things in very tightly. Another way of saying that is that it's very difficult to orthogonalize things in frequency. And when we get to OFDM, you'll see we do have a way to orthogonalize things in frequency. But it's very difficult in a traditional FDM technique, not OFDM, but FDM, to be able to keep the isolation between the channels. With TDMA, of course, everything is done by time slice. So each device, each user gets the channel, all the bandwidth of the channel for a very short slice of time. So if you're familiar with GSM or DECT telephone standards or even Bluetooth, these are all time division multiplex systems where most of you are probably familiar with Bluetooth. In Bluetooth, one of the most common ways they transmit voice is there's a time slot for an uplink, a time slot for a downlink, time slot for uplink, time slot for a downlink when they're doing voice. So that's basically a time division duplex. It's called TDD. This doesn't really show which is uplink and which is the downlink, but you could certainly imagine you could have downlinks and uplinks intermixed in a TDM system. The only problem with in a TDD system is that, like we talked about on the first day, if you're trying to transmit in one time slice and receive in the next time slice, you've got to allow for the speed of propagation between the two nodes. So in GSM, of course, the way they handle that is they put all the uplink time slices on one side and all the downlink time slices on the other side in frequency. One that's relatively new compared to those, although it's actually getting quite old now, CDMA was developed actually back in the 60s. And we could argue that frequency hopping code division multiple access was actually predates that. But the idea behind code division multiple access is by taking two different signals and encoding them orthogonally using two different orthogonal coding sequences, I can put them on the same medium and then at the other side separate them out. This seems like magic, and it kind of is, because to some extent you can get something for nothing out of a CDMA system. But you have to have sufficient signal noise ratio. The signals have to be orthogonal, and the power, you have to have a power control algorithm. If you've studied cellular, you know that CDMA cellular, you have to control the power here at the receiver. If this is, we're talking about going from this side to this side, the power at the receiver has to be controlled fairly tightly, because if one of these signals is much larger than the other, then you can't really pull the two apart. So that's CDMA. We don't use CDMA in Wi-Fi, so we're not going to spend much time talking about it, but obviously it's a fairly fundamental part of cellular systems. If you have a Sprint or a Verizon cell phone, the original 2G and even to some extent 2.5G was all CDMA. We've kind of moved into other things now, but the Sprint and Verizon systems were originally built on CDMA. And of course, since I work for Qualcomm, that's the technology we really commercialized. So we made a lot of money off CDMA. Okay. Any questions on that before we go to the next batch of slides? There's some fairly interesting stuff in here, and there's some stuff that I'm just going to cover for background, but really isn't part of wireless LAN, so I won't spend a lot of time on it. This is not a class on electromagnetics, so we're not going to spend a lot of time about antennas, talking about antennas, although I think it's important you have at least a little appreciation for antennas. Designing antennas is a magical art. The companies spend a lot of money hiring people. My last company, we spent $140,000 buying software tools to do antenna design, because it's really an esoteric art doing antenna design. But the idea is that, you know, as an antenna, you put power into it, it radiates the power out. When there are electromagnetic signals that impinge on that antenna, it turns it into a current that comes out the other side. What you really want to have is what's going in the transmit side is what's called good radiation efficiency, which means you want a significant portion of the power you put into the antenna get radiated out as an electromagnetic wave. Antennas have properties, and we'll go through this in more detail, but antennas have properties of gain, that they can have directional gain, so there's more gains in one direction than others. And in more modern Wi-Fi systems now, we do what is called beamforming, where we can take multiple antennas and change the phase of the signal going to those antennas and steer the energy in certain directions. So it's used, in fact, in our latest version of 802.11, we'll be doing we can accommodate up to 8 antennas, and we can use the 8 antennas either for MIMO or for beamforming. Every antenna has something called a radiation pattern. It's really usually depicted as a two-dimensional cross-section that shows which directions the energy is either being transmitted to, or as a receive antenna pattern where your maximum gain and minimum gains lie. The size of this pattern is arbitrary. Usually people will show antenna patterns as 3 dB contour or 10 dB contour or 6 dB contour or whatever, but it's really the pattern, the size of it is kind of arbitrary. Antennas have something called a beam width. So it really is it's a measure of how directional the antenna is. An omnidirectional antenna, well, of course, doesn't really make sense to talk about beam width for an omnidirectional antenna because it's designed. This is an omnidirectional antenna. It's designed to radiate antenna energy equally in all directions. And there's really a couple of different ways to think about this. There are antennas that are omnidirectional in azimuth only. So they have donut-shaped patterns. So basically, they radiate energy out horizontally. They don't do it in the switch vertically. You see these a lot in Wi-Fi access points. That's why I bring it up. That omnidirectional antennas that have either hemispherical or donut-shaped coverage are very useful for access points. An isotropic radiator actually creates a spherical wavefront, so it's omnidirectional in 3 dimensions. So you can think of antennas being either omnidirectional in 2 dimensions or omnidirectional in 3 dimensions. Generally speaking, I can't think of a good counterexample. A receiving antenna's pattern is the same as its transmitting pattern. In other words, the gains are the same whether it's transmitting or receiving. So, as I mentioned, this idea of a point source antenna that radiates equally in all directions as a spherical wavefront, that's called an isotropic antenna. And most of the time we'll reference performance of an antenna compared to an isotropic radiator. In fact, there's a measure called effective isotropic radiated power, EIRP, of an antenna. And that's what we do, is we compare the power of an antenna to an isotropic. Quite often in Wi-Fi, we will be dealing with either quarter wave or half wave dipole antennas. So you'll see a lot of times in an access point a little stub sticking up here. The thing about a quarter wave antenna, though, is it needs a ground plane to be able to radiate, because what happens is the wave that's created, I don't really have a picture of a sine wave here, but the wave that's created out this side of the antenna has to be is equivalently radiated on the ground plane. It's called antipodal radiation. So this looks like a half wave. This is a dipole. If you bought a FM radio, you know, sometimes you can go to the store and buy these little long-looking things that connect into the back of an FM radio. That's a half-wave dipole. And, of course, these have been known for years and years and years, so the antenna patterns are very well defined. So you can see this is kind of this donut shape. And that's, like I say, these are very common in Wi-Fi access points, because typically in an access point installation, you're going to try to cover a room or a part of a floor. You're not generally trying to go downstairs. You know, if you're in a home, obviously you are, but typically access points are designed with these kinds of antennas in them so that they're covering things basically out in 2 dimensions, and they're not trying to go up or down with the pattern. In fact, you can see with this dipole antenna, there's actually no signal that comes up off when you look straight down on that quarter wave, there's no signal coming out of it at all. It has very low gain vertically. Sometimes you'll see in building-to-building systems parabolic antennas. These can have much higher gain. I had the house we used to live in. When we first moved there, we couldn't get. They didn't have DSL there, so I had to have. There was a company called Skybeam that would come to your house and mount a parabolic dish pointed up at an antenna on a mountain a few miles away, and it was actually using the Wi-Fi bands, the radar bands for Wi-Fi. But they point that dish up at the antenna, and that dish had about 20 dB of gain. So the thing about a parabolic antenna is you can typically get much higher gains than you can with a dipole. A dipole is only going to have like 3 or 6 dB of gain, depending on how you got it set up. But these can have 20 dB of gain. Space telescopes can have even more than that. The gain is in fact proportional to the aperture size. So we quite often refer to antenna gain using this dimensionless unit, dBi of gain. That means dB of gain compared to an isotropic radiator. And antenna gain doesn't refer to obtaining more output power than input power, but rather directionality. In other words, if I put 10 watts into an antenna, gain doesn't magically give me 20 watts out, but it can focus the energy so that it looks like it's 20 watts if it's 3 dB gain in a certain direction. But you can't do that. You can't get that in all directions. So in other words, if I put 10 watts in an antenna, I can focus that energy and make it go in some directions, but I do that at the expense of being able to radiate power in other directions. So you can't get something for nothing. You're out of an antenna with gain. So that's really, this is kind of the key point here, that you get gain at the expense of omnidirectionality. You can't be both. You can't have both gain and omnidirectionality in 3 dimensions. So this kind of gives you an idea of, so the effective area of an antenna, that's something you can imagine. If we're talking about waves radiating through space, then the amount of signal you can get out of an antenna is proportional to the amount of area in that antenna that can capture that wave coming in, right? Because it creates currents in the antenna. So if I have a bigger antenna, I can generate more current in that antenna and get more current out of it. And so if I take a big dish antenna, I can capture a whole bunch of those waves coming in and focus them down on a point and pull that signal in. So I can actually, with a parabolic antenna, I can get much larger gains than I can with a half-wave dipole. But of course, it's very directional. And that's a problem, right? You wouldn't want to have to, when you use your laptop, you wouldn't want to have to aim your laptop at an antenna, right? That's why we don't really use parabolic antennas in consumer products. We only do them in fixed point-to-point links, typically. So there's a formula that gives us the relationship between antenna gain and effective area of the antenna. And this is it. Really not going to do a lot in here with this because, like I said, we're not going to be dealing with point-to-point links so much. But this is used in something called the Friese equation, or the path loss equation, so we kind of need this at least to understand. Now, I will say one thing. Note that the gain is a function of the frequency squared, or inversely proportional to wavelength squared. It's kind of a subtle point, but it'll come up later in path loss equations that as the frequency goes up, you get more gain out of an antenna of a given physical size as the frequency goes up. And you'll see that more in a minute. It's really a question of how many wavelengths, how many wavelengths of the energy are you coupling in. So waves propagate from one place to another in space. That's the next thing. So we talked a little bit about antennas. Let's talk about propagation modes. Ground wave and sky wave we don't really deal with in Wi-Fi because the frequencies are too high. These are only at lower frequencies. So in Wi-Fi, the 2 that matter the most are line of sight and non-line of sight. We talked a little bit about this last time. So line of sight, I can see the access point. Non-line of sight, I can't. The thing to note is that any time that an electromagnetic wave hits a boundary of a medium has a different refractive index, then you get a little bit of reflection and a little bit of refraction. So if you have an incident wave on a medium that has a higher refractive index, it'll refract going in, and you'll actually get a little bit of reflection as well because there's a boundary between the two media. Obviously, if you're in a vacuum in space, about 50 or 60,000 miles out in space, then there's nothing impeding the wave to slow it down. So we're closest to the speed of light in a vacuum, we should be able to propagate the waves at the speed of light in a vacuum. As we get into thicker and thicker air or other media, then the waves will travel more slowly. And you can actually see this refraction happen in practice. You can have actually waves bending as they go from one medium to another. Like I said, ground wave we only see at low frequencies down in the megahertz range, but this happens in AM radio a lot, that you'll see ground wave propagation. And if the soil is moist, if you live in a wet area, then an AM radio signal can travel pretty far actually using ground wave propagation. It's all based on soil conductivity. Skywave propagation, as you get a little bit higher in frequency up into the HF range, below 30 megahertz or so, then you can actually get bounces off of the ionosphere. Again, this is not something we typically do at Wi-Fi. There are other packet radio systems designed to work at HF. And there are other even more esoteric things if you're familiar with this. For example, I think it's the Forest Service uses meteor backscatter even. That as meteors come into the atmosphere, and there are always small meteors coming into the atmosphere all the time, they create ion trails. And anytime you have ions, that creates a charged boundary, you can bounce a radio wave off of it. So in remote areas where they're trying to monitor for forest fires and stuff, they can even bounce radio signals off of ion trails of meteors coming into the atmosphere. It's called meteor backscatter. So again, we don't do this on Wi-Fi because we typically are working at much higher frequencies, and you can't get a lot of bandwidth out of these. But it's just something that's interesting to note of how radio waves can bounce off ion layers. And in fact, if you're a ham radio person at all, then you may know that you can actually get multiple hops off the ionosphere and get propagation quite long distances around the world in these HF bands. So once we get up into the range where we actually have some bandwidth, about 30 megahertz or so, then we have to depend on line of sight propagation. You don't get ground wave or sky wave once you get up in those higher frequencies. So there's one thing I guess I didn't, that's, again, it's probably not relevant to a Wi-Fi class here, but when radio signals above 30 megahertz go through the ionosphere, because there is layers of charged particles in the ionosphere, they don't bounce off, but the polarization of the radio wave can turn as it goes through the ionosphere. We haven't really talked about antenna polarization. I didn't really mention it, but you notice in a Wi-Fi access point, the antenna sticks up. That creates an E field, an electrostatic field, an electromagnetic field. The idea is we want those end up being created at right angles typically. And that's called vertical polarization when the E field, electrostatic field, is vertical. And that's most of the time is what you see in Wi-Fi. And the reason that is that when a vertically polarized signal bounces off a reflection, it changes its orientation. And it tends to help block, if you put the vertical antenna on the wall there, any bounces off the floor will come back to it at cross polarization, so you have a little bit less multipath. Whereas if you turned it horizontally, it seems that the measurements show that you end up with a little bit more multipath. So vertically oriented antennas are used. That's why we use vertically oriented antennas a lot of times, is that it seems to do better for indoor multipath. So this is really something for long-haul point-to-point links. Again, not so much relative for this class, but something you probably want to have in your notes. And this is where we get into the good stuff. So as we talked about, what we have is a transmitter, we have a channel, and we have a receiver. And then there's a modulator and a demodulator on both ends of that. The channel is where all the fun stuff happens, because that's where the signal gets corrupted. And so we have to worry about all of these things that happen to the signal as it goes through the channel. There's certainly going to be attenuation as a function of distance because of 1 over r squared kind of path issues, free space path loss, just because we are propagating in space. We'll have noise, we'll have atmospheric absorption, multipath, refraction, and thermal noise. So we got all these things that impair the channel. We talked about some of these last time. We'll talk a little bit more about the path loss equation toward the end of the hour, but attenuation is higher at higher frequencies, as we talked about, as you saw on those curves last time. As you go up in higher frequencies, there's more absorption by concrete blocks and all kinds of building materials. So we end up having more absorption at higher frequencies, which is why we can't just move everybody to 120 terahertz and do all of our communications there. So this is kind of an important concept, is free space path loss. And free space path loss is the ratio of transmitted power to received power. And it's made up of, this is actually kind of a function of how much power is impinged on the receiver. It's obviously a function of distance squared. And these all, you have to be careful with units when you're doing all these things. And in your homework problems, you'll have to pay attention to your units. Oops, let's go this way. So if we redo this equation, so this is path loss, 10 log the ratio of transmit to receive power. Because there was a squared term here, if we take the log of that, that's 20 log of this quantity. So that's 20 minus 20 log the wavelength plus 20 log the distance plus 20 dB roughly. And so that turns out to be a path loss equation is a function of the frequency squared and the distance squared. And that's kind of the important thing to note about this is, as you go up in frequency, the path loss increases. As you go out in distance, the path loss increases. And both of those, because it's 20 log and not 10 log, then doubling the frequency will reduce, I guess I should say, adding 6 dB to the path loss is the same as doubling the frequency. So if you double the frequency, you have 6 dB more path loss. If you double the distance, you have 6 dB more path loss. So, which is why if you look at your 5 gigahertz access points, your dual band access points, if you go out and measure, and actually I've done this, I measured this in my house, and it was kind of interesting. If you look at the 5 gigahertz band compared to the 2.4 band, for the same transmit power, there is about almost a 6 dB difference in the received power. So 5 gigahertz doesn't, the coverage area for a 5 gigahertz access point isn't as big as for a 2.4 gig access point. It's the same transmit power and same antenna gain. That's kind of, these terms are, we didn't put those terms in here, and you'll see those in a minute. But fundamentally, the thing to keep in mind is that path loss is a function of frequency squared and distance squared in free space. Now, you can modify this equation to include antenna gains, transmitter gain, receiver. And there's also this thing called the effective area of the receiving and transmitting antennas, right? If I'm using a parabolic dish, then that gives me a lot more received power. I can also focus the transmit power. You don't see this so much. A lot of times in Wi-Fi link budgets, we don't include this so much because we normally, in a lot of Wi-Fi access points, will assume that the gain antennas are 0 dBi gain. So they're about the same as an isotropic radiator. So you can, but you can modify the free space loss to include antenna gains. To revisit some of the things we talked about last time, we also have to accommodate thermal noise. In satellite communications, this is especially a big deal because we're trying to operate at very long distances with very low margins. So you notice, well, let's just go to the next slide. So as we talked about last time, KTB is the amount of thermal noise here. And so for a Wi-Fi system, well, this is minus 174 dBm per hertz, like we talked about last time. And so what that says is that in a 1 megahertz channel, and actually a 10 megahertz channel, you're at minus 104, and a 20 megahertz channel, you're at minus 103 dBm. That's the best you can do, but note that that's at room temperature, 27 degrees Celsius. If you're trying to operate a satellite link, let's say you're trying to communicate with a satellite that's out, by Saturn or Pluto or even beyond the solar system, then what's the term you can really change? You can't change Boltzmann's constant. You have a certain, whoops, let's see, here we go. Nope. There we go. So you have a certain bandwidth that you need to operate to get your data out, and you want to try to keep that bandwidth fairly small. But the one you can really play with at your receiver is the temperature. And so what you see for deep space ground tracking stations, they'll cool the receiver down very, very cold, like liquid nitrogen temperatures or more, to get this T term and KTB down as low as possible. And that's what allows them, so when they're communicating with satellites out in the far reaches of the solar system, they're using a very large parabolic dish, focusing the waves on a radiator that goes into an amplifier that's cooled typically to very, very cold temperatures to get the KTB down as low as possible. And I didn't really do this example, but you could go back and rework this example. If you cool this to liquid nitrogen temperatures, you'd see that the noise floor drops significantly. Because the noise power is a linear function of temperature. So the closer I can get to absolute zero, the lower I can make the background thermal noise. And I bring that up because we do a lot of space work here in Boulder. So if you ever end up working on any of that stuff, that's an important thing to know, is that when you're working on a satellite tracking ground tracking station, those are always really cold. They run those receivers really cold. There's some other things that go on. If you have two different radio signals coming into a receiver, then if that receiver were perfectly linear, it would be able to allow those both to hit the amplifiers and mixers and everything, and there wouldn't be any problems. But in fact, there's always a little bit of nonlinearity in every circuit. And any kind of nonlinearity in the circuit, you end up creating intermodulation distortion. You can have unwanted coupling between signal paths. This is, again, is particularly if there's any kind of time misalignment or frequency misalignment in your receiver systems, then you can have crosstalk. As I talked about last time, impulse noise can be caused by things like spark plugs. And then in the unlicensed bands, we just have a lot of stuff there. So in the 2.4 gigahertz band alone for Wi-Fi, you'll also have Bluetooth there. You'll have cordless phones, microwave ovens, baby monitors, all of those things, even cordless phones. Those are all, especially cordless phones. And I'll tell you a little aside here. I don't think they sell it anymore, but Panasonic used to make this cordless telephone that operated in the 2.4 gigahertz band. It was direct sequence spread spectrum. So it was spread out over several megahertz of bandwidth. And it turns out it was a great denial of service attack on Wi-Fi. Because if you took that cordless phone and just pressed the off-hook button that caused the link to be set up between the handset and the base station, it would kill whatever Wi-Fi channel it was on. It really was just a really broadband noise jammer to the Wi-Fi. So it's so funny to me to see people get really involved in all these hacks on Wi-Fi that try to do denial of service, when in wireless, really, to do denial of service, all you really have to do is just create enough interference that they can't close the link. That's a lot easier than trying to do fancy denial of service attacks. That means that, though, if you're responsible for trying to keep a network up and somebody's decided to mess with you by putting some sort of noise source right near your receiver, then they can potentially shut down your network. It's not that hard. So it's funny to me. We'll talk about quality of service in here. When we try to set up latency and jitter bounds on packet delivery. But in fact, quality of service is an oxymoron for wireless. You can't really guarantee quality of service because of all these factors in the channel that can disrupt the packet delivery, including just a jammer blasting away and corrupting your link. The final thing to note here is that, and this is most relevant in radio telescopes especially, is when the antenna is coupled into the front end of the whole receiver chain. It's called a low noise amplifier. So as I mentioned the other day, this can be femtowatts of power. So we've got to get that boosted up by several orders of magnitude to get it into the receiver processing system. That first amplifier is very critical, the noise figure of that. So it's pretty typical for Wi-Fi systems to have an additional 4 to 5 dB, even 3 to 5 dB of noise added to the signal as it boosts it up in that initial low noise amplifier. And that really says, so if we go back to KTB is minus 101 in a 20 megahertz bandwidth, if the noise figure of this receiver is 4 dB on top of that, then what that says is you've already, your absolute floor now is at minus 97. You can't do any better than that. And the only way to really reduce the noise figure of this receiver is by cooling it down. So if I cool this thing down to, way down to near absolute zero, then I can reduce the noise figure in the LNA, and so that cuts down on my KTB across the whole receive chain. But obviously, nobody wants to take a cell phone and put liquid nitrogen in it, so it's kind of not practical. So we don't really deal with that in laptops and cell phones. So we just generally live with the 4 dB or so of noise figure in consumer products. The other thing here is we need to start working our way towards talking about bit error rates and bit errors and packet errors. So there's this thing called EB over N0, or EBNO, as people call it. It's the ratio of the energy per bit divided by the background noise. And this could be man-made noise, but the best you can do theoretically is KTB. So EBNO really lets you set this is also called the signal noise ratio, because it's the signal power to the noise power, ratio of signal power to the noise power. Sometimes you'll see us talk about energy per symbol. If there's more than 1 bit per symbol, so if you have 2 bits per symbol or 4 bits per symbol, then you sometimes will see the ratio of energy per symbol divided by N0. But in any case, this EBNO is what's required to achieve a desired at a certain data rate. So, for example, QPSK in your homework problem, QPSK, that's sending out 2 bits per symbol. So there's 2 bits. Every time you send a symbol, you're sending 2 bits. That requires a certain signal noise ratio for it to give you a given bit error rate. And so there's a relationship between bit error rate and signal noise ratio, or EBNO. As the bit error rate increases, then you have to increase the power to maintain the same EBNO, right? Because energy per bit, as your bit rate goes up, then your bits get narrower, so you have less energy per bit. So the only way to maintain the same EBNO is to increase the power so that you maintain the same energy in that bit as the bits get smaller and smaller. So that leads to something called the receiver operating characteristic, or ROC. And you'll see this a lot, and this is in fact the MATLAB thing in your homework exercise, where you look at the relationship. This is EBNO in dB, so this is signal noise ratio in decibels. And this is the bit error rate. So this is the probability of a bit error. So this is like 10% bit error rate, also called 0.1 probability of bit error. And so this says that this is a probability of errors being 1, which is pretty bad. So you can see that as you increase the signal noise ratio, then the bit error rate goes down, as you would expect. So if you go back to that eye diagram we looked at the other day, what that says is that as the signal noise ratio increases, the eye is opening up wider, so it's much easier to decide where the bit boundaries are, whether it's a 1 or a 0 you're transmitting. So this figure is for binary phase shift keying. We haven't talked so much about that, but BPSK is where you basically are just sending 1 bit per symbol, and you're either toggling between 0 or 180 degrees in phase. We can also do 90-degree phase shifts in SIN modulation. That's QPSK. 16 QAM is actually 16 levels per symbol, which is 4 bits per symbol. And then 64 QAM is 6 bits per symbol. So you can imagine, like we were saying, if you think about the eye diagram, if I'm trying to transmit more levels, if I'm trying to transmit 4 levels or 16 levels, then now you've got to have a much higher signal noise ratio to maintain the same bit error rate. And that's what you can see in this receiver operating characteristic. Okay, questions on that? So one of the things, the way we normally measure performance of a wireless LAN system, however, is with packet error rate. And packet error rate is, if you look at the 802.11 specs, everything is done in terms of packet error rate. But it's packet error rate with a 1,000 byte packet, so 8,000 bits. So if you look at the 802.11 specifications, it'll say, for example, that for the lowest data rate, which is called modulation encoding scheme 0, MCS 0, that you have to provide a sensitivity of minus 82 dBm to achieve 10% packet error rate with 1,000 byte packets. So for that case in 802.11, if we say 10% packet error rate, what does that equate to in terms of BER? Well, so 10% packet error rate is 0.1, and then if we plug it into this formula, 8,000 bits, then if we rearrange that, that works out to about a 5 times 10 to the minus 6 bit error rate. And so that's why, you know, 10% packet error rate sounds pretty bad, but it's for 1,000 bytes, so it's 8,000 bits. So that says that's the probability. I mean, if you have just 1 bit bad out of those 8,000, then the whole packet's corrupted, right? You can't. So, so in the early versions of 802.11, all we did was do a cyclic redundancy check. We just checked to see were there any bit errors in the packet. So if you send 1,000 bytes, if there are any bit errors in there, then you throw the whole packet out, and you basically wait for a retry. And it turns out, you think 10% sounds like a pretty crappy channel, but in wireless, a 5 times 10 to the minus 6 bit error rate's a pretty decent channel, actually. And so if you actually, if you actually took a tool and measured the throughput, you'd see that a lot of times in Wi-Fi, if you're in a crappy environment, you're doing worse than 10% packet error rates. And what happens is in Wi-Fi that we try to do rate adaptation. We're always trying to, the access points have algorithms in them to try to maintain the packet error rate within reasonable limits. So it'll lower the modulation rate or make the fragment sizes smaller, or it'll do other things in the access point to try to keep the packet error rate within acceptable limits. But like I say, this sounds like a lousy channel, but it's really not that bad. It's not an, and so what we've done in more modern Wi-Fi systems is once we went to OFDM, we put forward error correction in there. And now, instead of just detecting errors, which is what we did in the beginning, we actually can correct errors. And that significantly improves the performance of the system because we can correct errors in the bit stream before we recreate the packets. And so if you look at, this is from an 802.11g specification. This is a 20 megahertz bandwidth, 6 megabits per second, which is the lowest modulation encoding scheme for 802.11g. That's minus 82 dBm for 10% packet error rate. That's the spec. And you can see that as we go up in speed, the sensitivity is less for the same packet error rate. Kind of makes sense, right? Because you would have to have higher signal noise ratio to maintain the same bit error rate or packet error rate because the bits are getting narrower. So you have less EBNO, smaller EBNO. So you can see at 54 megabits per second, minus 65 dBm. So there's a swing here of, 17 dB between these two. So you have to have 17 dB more power to operate at this speed than at this speed for the same packet error rate. Other impairments. In the Wi-Fi systems that are fairly short range, you don't see so much atmospheric absorption. The latest versions of IEEE specs talk about 60 gigahertz. We talked a little bit about millimeter wave the other day. Millimeter wave bands are unlicensed because it's an oxygen absorption band. The resonance of the oxygen molecule is right around 60 gigahertz. And so if you try to send 60 gigahertz outdoors, there's more attenuation. You don't see this until you're trying to go like a kilometer or more. But water vapor and oxygen both attenuate, especially the higher frequencies, much more heavily. See? Yeah? No. Multipath is probably one of the most common impairments that we see in an indoor system like this, and we'll talk a lot more about that as the class goes on. And then refraction, you saw that earlier, but we really don't see. In Wi-Fi, sometimes we can see refraction around sharp objects, like if there's a filing cabinet. You can see some refraction around the edge of a filing cabinet or something like that. But it's not really as much of an effect at Wi-Fi frequencies. So this kind of shows you visually those three different mechanisms. So you can reflect off a boundary, you can scatter off of an object, so you can have specular scattering. And this happens especially at millimeter wave, you get a lot of specular scattering. And then you can have diffraction around an edge. Because you could imagine at higher frequencies, like at 5 gigahertz, 5 gigahertz is mostly line of sight. So if you're trying to go past a metal filing cabinet and you put your laptop here, you wouldn't normally expect it to work unless there was enough energy kind of diffracting around that. And you're actually usually indoors, you're getting so much reflection. It's amazing to see how much of the energy is actually being reflected into your laptop, especially in a non-line of sight scenario. So if the access point's outside, what you're getting, especially with OFDM, is you're getting all the reverberations. It's collecting that and trying to accumulate all that energy. It's one of the advantages of OFDM that we'll talk about more. So refraction, diffraction, and scattering. Scattering happens a lot in millimeter wave. So to try to set us up to talk about MIMO and OFDM and things like that, spend a little bit of time talking about multipath propagation. So multiple copies of signal arrive at different phases. So again, the access point over there, it sends a signal out. That signal is going to bounce off that wall and this wall and the ceiling and the floor and all of you and the chairs and everything else. So there's all this scattering that's happening in the room as the signal reverberates around. This leads to intersymbol interference, right? If these reflections are arriving at my receiver after the end of the bit time, so if I send a bit out and the reflection is still arriving when the next bit time is supposed to start, then that's an intersymbol interference. I'm getting interference between the previous bit and the next bit. So that's a problem. Fading, if you've taken the cellular class, you know that fading is a big deal in cellular because they have fast fading and they're typically in a mobile environment with a very rapidly changing channel. In this class, we're going to be mostly focused on selective fading, flat fading, and slow fading. And as you can imagine, the ways we get around all these impairments are try to use forward error correction. We can try to use adaptive equalization, or we can use diversity techniques. Diversity techniques means either transmitting, like we talked about when we were talking about the antennas the other day. Diversity means I can have two different antennas in different locations in space, or I can use two different frequencies with one antenna. That's frequency diversity. So space diversity is two antennas. Frequency diversity is two different frequencies in the same antenna. And then we have time diversity, where you transmit the signal and then you transmit the signal again. Now, obviously, if you're not moving, if nothing's moving in the room, then transmitting the same thing twice where it gets corrupted the first time. Time diversity doesn't help in a channel that's not changing. You have to have a channel that's changing for time diversity to do any kind of good for you. So that's the main three kinds of diversity: time, frequency, and space. So forward error correction adds redundancy to the bits. The most common forward error correction used in Wi-Fi is called convolutional codes. Typically we'll add almost a 50% overhead. So that 6 megabit version I showed you a minute ago, 6 megabits Wi-Fi using OFDM, it's actually transmitted at 12, but there's twice as many bits sent. So it's called a rate 1/2 system. So the actual data rate you get out of the coder is only half of what goes over the air. So that extra redundancy, sending twice as much information, is used to correct the errors in the signal. So we'll talk about in here in Wi-Fi rate 1/2, which means you're sending twice as many bits as you need. Rate 3/4, which means if you're transmitting at 12, you're only getting 9 in because the other 25% is used for redundancy to error correction. So that's called the rate of the code. We'll talk more in details about that. But that redundancy, error correction requires redundancy. You have to transmit extra bits to get error correction. So that's all that. And in addition to forward error correction, we still use error detection. So we'll still check for packet integrity even if we do forward error correction. So if the error correction system can't correct all the errors in the packet, then we can still detect that there was a problem. And actually, we don't acknowledge it. 802.11 is called an acknowledged system, an ACK system. So if you don't get the packet successfully, then you don't transmit anything. You just wait for it to be transmitted. Adaptive equalization. This is usually some fairly involved signal processing, but it basically looks at trying to learn the characteristics of the channel and then compensate for it in the signal itself. Usually that's digital anymore. And then more detail here on diversity. So individual spatial channels experience different fading events. Like we saw last time, 2 different antennas are going to see different channels if they're more than half a wavelength apart. So I can have space diversity, frequency diversity, or time diversity, which is why, if you look at these access points, why they have multiple antennas. Now, today, we have multiple antennas in there to do beamforming as well. So if you have an 8x8 system, we can use 8 antennas for beamforming. But in 802.11g, there was no beamforming. All you really had was these 2 antennas. And in 11g, during the preamble, the beginning of the signal, it would listen to this antenna, monitor the bit error rate, look at this antenna, monitor the bit error rate, and by the end of the preamble, whichever of the 2 antennas provided the best signal was the one it used for the rest of the packet. So that's called switched spatial diversity. So you can imagine that this gets to be fairly complicated, right? Because in any environment like this is a very complicated environment for electromagnetic wave scattering. And so you'll end up with a direct path. You'll end up with this is called a two reflector or 2-path reflector. This is a very simple example, but even with this, you can end up with if these are moving relative to each other, having some significant fades in and out as you go through, as devices move through just even a 2-reflector model. So this is something, especially in cellular systems, where there are companies like LCC that get paid a lot of money to do large-scale ray tracing. If you've ever worked around cellular or plan to work around cellular site planning, they do some very sophisticated modeling using ray tracing because it's big money, right? Where you place cellular base stations can have you can end up with making a huge hit on your capital equipment costs if you don't put those in the right spots. In Wi-Fi, we still use those tools, but Wi-Fi access points are a lot cheaper. So a lot of companies will do some site modeling and then stick in extra access points as they do site surveys to see if there are any dead spots. I think I've said all this pretty much. So we've learned a lot. So we've covered a lot of things about what happens into the system. We have, all these different error things. We have channel conditions. But all of these are things that can happen to the signal and things that we need for, like we need certain signal noise ratio for a certain bit error rate. We've got transmit power. We've got a channel. We've got all this stuff. What does that mean from a systems perspective? And that says we have to come up with a model. We have to come up with a model for, can we model the multipath? Can we come up with empirical models for the multipath? And this is actually what's called the exponential model. So I can have, if I assume that all these different reflectors are out there and they reflect it with different strengths, I can show these, set this up as sort of a sum of different reflections. And that's what really ray tracing does, is that it tries to calculate the a delay and a complex gain for each reflection. And we're really not going to do much with this, but you need to at least be aware that this is what we try to do. We do modeling of each of these reflections as a complex reflection coefficient as it comes off of a boundary. And that leads us into what's called flat and frequency selective fading. So there's a couple of terms that we need to be familiar with here. delay spread is one. We'll talk a lot about delay spread. So as I've said, you know, if you have an access point on the wall and it sends a signal out, that signal to your laptop will propagate the shortest distance will be the direct path if it's a line of sight system. And then you'll start seeing all these reflections. If you measure the reflections, let's say you send an impulse out from that, just like you were in a tank of water. If you dropped a rock, you would see the wave send out, and there would be the wave that reaches the receiver first, and then there would start to be all these reflections. So we need a way to quantify how many reflections there are and how strong they are in an environment. And delay spread is that. Delay spread is a measure of how strong the reflections are and when they occur. More formally, mathematically, it's the centroid of the observed reflections after the main path. The inverse of the delay spread is called the coherence bandwidth of the channel. And for a Wi-Fi system, this delay spread number that we talk about, which is sort of the average amount of time it takes a reflection to reach a receiver, is on the order of 50 to 100 nanoseconds. So that's a key point because, well, you have to use that in our system design. Now, we talked about last time that you can have a channel that has all sorts of variations across the channel. That's called a selective fading channel. And that's a selective fading channel basically has delay spreads that can be fairly short compared to, well, this is better showing a picture. So this is in time. If you compute the spectrum here, you can see this has a lot of frequent variations in the frequency domain. So this is a frequency selective channel. It's got a lot of changes in the frequency content over the bandwidth. This is 200 megahertz here. In this case, this is a 40 megahertz channel. If I tried to use just this part here, this is a flat fade because everything is kind of dead inside that bandwidth. And you could sort of imagine the way to think of coherence bandwidth is sort of the distance between these peaks and nulls in the frequency domain. It's another way to think of coherence bandwidth. So this just shows one example of a mobile system where the delay spread, this is an outdoor mobile channel, so the delay spreads are much higher, like 1 microsecond. So again, it's not unusual in cellular to see delay spreads like maybe an order of magnitude or a couple orders of magnitude bigger than an indoor Wi-Fi channel. So I think we've already kind of said this. Fast fading and slow fading aren't so much of an issue here, but flat fading is when the channel is attenuated across the whole band of interest. Frequency selective fading is there's multiple fades in and out and across the band of interest. And so in 802.11, we've tried to come up with ways of modeling this. And I'm not going to spend a lot of time on this because you're not really responsible for these formulas. But fundamentally, we try to model these as exponentially decaying reflections. And what that really takes us to is something called the link budget. So we'll try to accommodate. Let me back up here. There's another way to think of this, and that is if you look at the path loss. This is the way we typically draw path loss. And so if it's 1 over r squared, then the path loss would have a roll-off of 20 dB or 6 dB every time you double the distance. So, but in fact, if you go out and make measurements, this is not what you get. That in fact, you're going to have some that are less and some that are more. So in fact, actual measurements show this as being a very noisy thing. And that's because of all the multipath reflections. Sometimes you're in a fade, sometimes you're not. So if I put an access pointer on that wall over there and then took a receiver and just started walking straight away from it, then I would get something that looks kind of like this. It would actually be steeper than 1 over r squared. But there'd be all this variation from measurement to measurement because I'm going through multipath fades. And so I have to, the way we typically accommodate that in the path loss equation, and we'll spend more time talking about this, is that you can apply a standard deviation. You can look at the standard deviation of the observations at a given range. So the path loss will be a certain number of dB plus or minus a few dB at a given distance from the access point. So this leads us to something called the link budget. And this is actually a fundamental thing in doing communication systems design. You may have seen it in other classes. But you start at the transmitter and say, okay, this is how much power I'm putting out. The transmitter antenna has a certain gain. There's a center frequency, because remember, path loss is a function of frequency as well as distance. So path loss at 1 meter is 44.2 dB. Remember, we talked about the path loss equation last time. So that's that PL at 0, PL 0. So that's at 44.2 dB for this particular frequency. So path loss at a certain distance away, 20 dB at 10 meters, 12 dB at 4 meters, 6 dB at 2 meters. So you have, this is just showing path loss. Then at the receiver, you have a certain gain. So if you take the transmit power minus the path loss, that's the power at the receiver. So that's the best you can do given path loss. So that's where you start with. And you say, okay, the noise power per bit at the antenna, that's a function of KTB. This is the noise figure of the receiver. So again, I can't do anything unless I cool that amplifier down. This is kind of fixed. So now if I subtract those off, then this is the noise power per bit that's coming out of the low noise amplifier going to the demodulator. For a given modulation scheme, you've got to have a certain EB over N0, EBNO. And so if you saw in QPSK, if you want 10 to the minus 10% bit error rate, you've got to have a certain signal noise ratio. So in this case, for these modulation schemes, these are the required signal noise ratios. There's something we haven't talked about called implementation loss, and that has to do with your ADD converters may not be exactly right. The AGC may be not boosting your signals to use all the ADC range. There may be imbalances in the receive chain where you're not down converting the frequencies properly. So these are implementation losses where things aren't working ideally. That's not unusual. That to be about 2.5 dB. And so when you add all those together, you end up with what's called a link margin, which says this is how far you are above KTB and plus the noise figure. So in this case, I can run and say, well, I've got 6 dB of link margin. So by the time I run through the whole path from the transmitter to the receiver and figure out how much signal noise ratio I need, I have 6 dB left over. And that says that I can't handle, for this distance, I can't handle any more than 6 dB of losses in addition to that, or I break my bit error rate. So this is the link budget, and this is what you work with when you design the communication system. And it kind of ties into one of your homework problems, is that you got to figure out some things you can control and some things you can't. If you can turn up the power, then you can buy yourself more link margin. If you can use a modulation scheme that doesn't need as much signal noise ratio, you can increase your link margin. So there are you can add antenna gain, and that'll increase your link margin. So what you can't allow is your link margin to get less than 0, right? If your link margin is less than 0, then your link doesn't work. You can't meet your design constraints for your system. So link margin always has to be bigger than 0, or your link won't connect. So I think that was it for today. And I think my voice is about done anyway. Any questions? All right. So like I said, stay tuned. We'll have a student assistant by the time you come back on Monday. Your homework assignment is due a week from Monday, so you should have plenty of time to work on that. I think we covered most everything you need to get to work on that. And I don't know, anybody have any questions before I cut you guys loose? No? Okay. All right, thanks a lot. We'll see you on Monday.